Hello and welcome back to Calculus 2. As you already heard, it's 9.2. It was a spoiler. Properties of power series. So tonight we are going to take a look more in depth at the general power series. So we have summation ck of x minus a to the k. You can start anywhere. Let's start at 0. And I'm going to first talk about the difference between one that has x to the k and one that has x minus a to the k. So it is important where we center the power series. So this a is the center of power series. A is the center power series. Now, what does that mean? Remember that in the formula for coefficient ck, if you do Taylor expansion, you have f function computed at a, then you have the derivatives computed at a, so all of them are computed at a. Once we computed those numbers in approximation, that was the point that we can compute without calculator. So if we are supposed to find the square root of 15, a was 16, because that was the easy point to compute. So we centered our approximation at 16. You want to set your power series expansion close to the portion of the function that you are observing, because the error piles up quickly if you are far away from the point that you want to observe. So if I am to, let's say, if I am to take that expansion of, let's say, f of x is equal to square root of x, right? That's the function. And we want to compute the square root of 15. Imagine if you were looking for the tangent line at 0. You're looking for tangent line at 0. Well, guess what? You're not even going to find one, because the derivative of square root of x is 1 over 2 square root of x. So you're losing that point in your domain. So the derivative is 1 over 2 root x. And if you look at this, right now you try to do the expansion around x equals to 0, you can't compute. You can compute the first term, but every other term after that is going to be not able to compute because you have a equals 0 in denominator. Let me just one more time give you the linear. This is just the first two terms. So f of a plus f prime at a x minus a. So if you are expanding square root function around 0, right, it's going to be an issue because you will have to compute 1 over 2 square root of a, and if a is 0, it will fail for that computation. So we cannot compute at all. Now, you can get a little bit better if you say, well, okay, 0 is bad, let's compute at 1. You would be able to do it, but the result that you get would be terrible, because remember what you are trying to do. You are trying to take a look at the square root function that looks like this. Here is your 15, right? And here's your 16 right after that. And here is your number 1. You make a tangent line here. It's a terrible tangent line. Just give me an hour. I'll be right there. That's the tangent line at 1. Now look at the value that 15 gives you and look at the value that the tangent line at 1 gives you. Garbage, right? Complete garbage. But 16 is close to 15 and easy to compute in this particular function. And if I draw the tangent line there, which is our Taylor expansion, which is our linear expansion, all of these approximations, then you see, here I'll zoom in, that the value that 15 has is very close to the value that tangent line has. Y value-wise, right? So looking at the power series, it is extremely important where you are centering your power series. You want to center the power series expansion, which is figure out what this A should be, at the point that it's close and in the neighborhood of the portion of the function that you want to observe. Now, some of you took physics, a little bit more advanced physics, let's call it engineering physics at RVCC, and you probably heard that before, simple harmonic motion. And you saw some formulas and so on, and they say to make the simple harmonic motion easy to compute, isn't a contradiction of terms, right? Simple harmonic motion is difficult, right? To make it easy to compute, replace sine x with x. What? What do you mean? Replace sine x with x. But then they say for small angles. So now there is another part that we can explore. So physics says replace sine x with x for small angles. The hell does that mean? Well, let's take a look at the graph. If I draw sine function, which is going to do the wavy thing forever, and then I draw the y equal x function, which looks like this, whoa, they're pretty much the same, right, in this small region. And then they diverge. So now we know that on the x-axis we have those pi values, right, which is your input, which is your theta, technically. So when I write here there is pi over 2, which is at 1, you know what, if you go pi over 6, maybe all the way to pi over 4, you can check how much that is. The values that you get from the f of x equals x and sine x are very close. So you are okay to approximate sine x with just x. Can you do better? Oh, hell yes. Because the Taylor expansion will actually help you do much better if you add more terms. If you spend some time trying to figure these things out, you probably found out that expansion for sine x is x minus x cubed over 6 plus x to the 5 over 120 minus x to the 7 divided by whatever the hell 720 times this is 1,400 something, I don't know, whatever 7 factorial is. There you go, done. So, and it goes in that pattern. It picks up all of the odd exponents and it goes the same factorial in denominator. That's your sine expansion. Now look, they said, let me just give the first term. But observe the next one, x cubed. How does the x cubed graph looks like? Does it look like exactly like this? So this next term will make this red line bend. It will make the red line bend around the sine and start following it a little bit more. But remember, x cubed is just going to make one bump and go forever down, right? And it's going to be bad now here. But that's the next term to the fifth to bend it back up. So this wavy behavior, as you add more and more and more of these terms, it's going to keep making this polynomial oscillate and bend on top of the sign. And it's going to go like that. Now, imagine that you need to compute something over here. And you go, right? You have to compute something around, I don't know, 4 pi value. And you go, well, now I need, 15 terms. Your factorial is in millions. No, you just shift with this A. You center it at 4 pi. And then you move these things around. So the first part that we are understanding now for power series is this A. And guys, this A is as simple as your precalculus shift the function to the left or to the right. That's that value. So what happened here? Remember, for the square root, we said, well, we're going to do this for A equals to 16, and it's x minus 16. Yeah, that's the whole thing is shifted to the right, 16 units. That's all it is. It's nothing special. Not higher order of mathematics. It is that basic concept from your precalculus 1, shift the function to the right 16 units. Or, over here, maybe shift it to 4 pi or whatever you need to. So that's the notion of that A. It's the center of the expansion. And then you go from there. The next huge part of the property of the power series is its interval of convergence and radius of convergence. So that's the next part. So what are we talking about? Well, let me go back actually to the sign over here, and we're going to realize that just over here between these two red parentheses would be the interval of convergence where these guys match up, right? The convergence can happen at the point, at the interval, and can happen over the entire domain. And the way we check for these is simply using the ratio test. So I'm just going to put over here in parentheses ratio test. You will always use that. And the ratio test will reveal to you the interval of convergence, and then you will take half of it as a radius. So let's take a look at these 3 examples. Now, I usually don't like to use the examples from the textbook because you know all the letters and you can read them. But this time I have to, because I don't want to go into the problem section and try to fish out 3 problems that will have this exact property. All of these problems here that are presented are for one of the cases. So one of them converges at the point, one of them converges at the interval, and one of them converges everywhere. So I'm just going to go slowly and redo these problems, even though, and then we'll probably do, another example from the homework to see whatever random example, whatever. So first one we're going to consider is x to the k divided by k factorial. Now, we're not using ratio here just because of factorial. You hopefully know that by now. We're always using ratio test to show convergence of power series. So always use ratio test. Next problem has no factorial, so it's good. All right, so how do we use ratio test? Well, we create the k plus 1 term, and then we divide k plus 1 term by the k term, and we take the limit. So limit k goes to infinity And I'm going to put these absolute values with red. Extremely important now. You cannot do these problems if you don't have them. We have x to the k plus 1 divided by open parenthesis k plus 1 factorial. And then I'm going to immediately times and flip the original one, k factorial over x to the k. And close the absolute value. So now we have limit. Don't forget the limit from each step, -5 on each problem. No, per step, -5 per step, you forget the limit. Yeah, I know, your exam could be like -30. X to the k divided by, remember, we are peeling off k plus 1 and then leaving k factorial behind, times k factorial divided by x to the k. So this is all the factorial talk. K's die, x to the k dies, and we are left with the limit. K goes to infinity, absolute value of x over k plus 1. That's all that it survives. Now, limit operates on x or k. K. So what is the variable in the problem? K. Which means x is constant in the eyes of the limit. Right? In the eyes of the limit, x is the constant. And what can we do with constants? Kick them out, right? So this x will take its absolute values and be kicked out. And you are left with the limit 1 over k plus 1. You do not need absolute values anymore because you know all of these k's are positive numbers. Right? K is the counter. Remember 8.1? K starts at 0 or at 1 and it goes 1, 2, 3, 4, 5. Nothing in between. These absolute values are important for x, not for k. X is the one that is carrier for these absolutes. And then what's the limit of 1 over k? 0. Nice. So now the answer over here is 0, which is always less than 1. So this power series converges everywhere.
What do you mean converges everywhere?
On the entire it's, as you can see, the condition for convergence of a ratio test is that whatever limit you get needs to be smaller than 1.
Okay.
We got 0. 0 is always smaller than 1. Therefore, the power series converges. Ratio test said it's convergent. So it's converging everywhere.
Converging to 0 everywhere.
No, just convergent everywhere. Now, what we are going to write here is that, and this is the part of your answer, interval of convergence is negative infinity to positive infinity, and the radius of convergence is infinite.
How do we know those things?
Because it's convergent everywhere. For all x.
How do you know it's everywhere?
Because this ratio test says that if the limit works out to be less than 1, it's convergent.
Why everywhere?
Regardless of x. You pick any x here. No matter what x you pick, it will always, the limit will always be 0, which is always less than 1. And x spans from negative infinity to positive infinity. Remember, x is the regular variable that you know from your, I don't know, 6th grade up to today. So that x has its domain from negative infinity to positive infinity. I do not have, you can also think this way, I do not have any restrictions on x. X can be anything, and this power series will always be convergent power series.
Question.
Just.
This power series converges everywhere because 0 is less than 1. Not because it's 0, because 0 is less than 1.
Condition for the, yes, condition for the ratio test is that limit has to be less than 1. So if this worked out to be 1/3, this, let's say 1 over k plus 1 worked out to be 1/3 for whatever reason, we would have an issue there. Because
the 1/3 is less than 1, but it's not 0.
Yeah, but then we would have to compute. Actually, when you see all three examples, the perspective will change, because right now you just have one example and you really have nothing to kind of grab on to see what is actually going on. The second example is, I believe, better in terms of, let me just see, yes. Second example is better because second example is giving you something to think about. So let's work on the second example. Bless you. So let's take a look at the second example from 0 to infinity. And we have negative 1 to the k, x minus 2 to the k, divided by 4 to the k. Let's just pile stuff up. That's it.
Why not?
Why not? So now, we immediately do the ratio test. Don't forget absolute values, otherwise it's a problem. Absolute values are going to kill this negative 1 to the k term, right? Do we all agree? Because that is going to be firing negative 1, 1, negative 1, 1, negative 1, 1, and absolute value will be stripping off those negatives every time. So there is absolutely no reason to write that term at all. We'll just ignore it. X minus 2 to the k plus 1 divided by 4 to the k plus 1 times, I'm immediately flipping the second one, so we don't have to write 5,000 steps. Let's write next one. Next one is where we peel off. We peel off x minus 2, and then you have x minus 2 to the k. We peel off 4 times 4 to the k, and then you have 4 to the k divided by x minus 2 to the k. Limit. K goes to infinity. Now a bunch of these terms are going to die. There we go. And we are left with absolute value of x minus 2. I actually don't need those parentheses. Divided by 4. What happened? Well, now we're observing this, and we realize there are no k's to apply the limit, so it's just this. This could be both.
Both what?
This expression that you see now, and this is the key. If you understand this, you're done. That's it. You understand this one now, you're done. This expression that it's left after we're done with the limit and the whole procedure, this expression can be either less or more than 1. What it depends on? It depends on the value of x. Now, what we are going to do is we are going to force this to be less than 1. So I'm going to say over here, we are forcing less than 1. Because I am looking for convergence, okay? I'm looking for all of those x's that I can pick so that this is convergent. I don't care about divergent series, because divergent series, they don't make stuff work, they make stuff explode. So if I want to have engineering, want to talk about making computers and stuff, I need convergent series. So we go through the ratio test procedure, we get through the limit to the point where we have an expression that is now dependent on x. This expression could be both larger or smaller than 1. We are only interested when it's smaller than 1 because that is when it converges. So you write this part here. Earlier was easy, 0. 0 is always less than 1, so it converges everywhere you're done. Now, you have an inequality from your algebra 1 that you actually have to solve. You solve this inequality, and you will come up with the values for x for which this series converges. So now, we go to the next line, and we solve this algebra inequality. You have absolute value x minus 2 over 4 less than 1, which is written as negative 1 less than x minus 2 over 4 less than 1. That is how you expand, if you want to use that word, your absolute values. I'm going to check if the stream is moving. Yes, it is. Good. It's been really spotty last week. And now what do? Multiply by 4, add 2, you're done. So times 4 everywhere. And then add 2 everywhere. And there it is. This one is called interval of convergence. Interval of convergence. Pick any number in there. The power series will converge. Pick anything out of it, it will diverge. And it is oh so easy to show that. Look at this. Oh, first of all, what's the radius of convergence? Clearly 4, right?
How do you know that?
6. Well, if you think about it on the number line, here is negative 2, here is positive 6. They are 8 units apart. Half of that 4 this way and 4 that way, right? So that will be the radius. And also note that this over here is 2. Your good old A equals 2, the center. All of that has to line up. Otherwise, stuff is terribly wrong. If you get anything else other than that 2 as the center of the... So when you're done through the entire procedure, you come up with the interval of convergence. If that thing is not in the middle, rip the page and start over, all right? Well, if it's test, erase it and then start over. Because, yeah, it has to be. It has to be centered at A, whatever you had x minus up there. So radius is 4. Why? Because from negative 2 to 6 you have 8 units. Half of 8 units is 4. So radius, half of the whole thing. Now, I want to look at... so this is a check. And hopefully you will connect some dots. Series negative 1 to the k of x minus 2 to the k divided by 4 to the k. This is the original series, right? Give me a number outside of the interval up there.
7.
Thank you, 7. Perfect value, 7, okay? So, what do I have for x equals 7. I have summation -1 to the k, and then 7 minus 2 is 5 to the k over 4 to the k. Do we see 5/4 to the k? Right? What does that do in divergence? In the geometric series? Geometric series? Divergence, right? Pick anything in a convergent region. It will give you convergence through geometric. So what are these power series? Do you see how power series is, quotes, air quotes for the stream, function, right? You have 1 plus 2, 2 plus 2, 3 plus 2, 5 plus 2, 10 plus 2, x plus 2, right? So as I think I made this point last time I talked about this. Regard sequences as your numbers for the math you did so far. So number 7, number 30, right? You know the numbers. So that's the correspondence. Sequences and numbers. Then your mathematical operations together with series. Series is the sum of the sequence. Well, addition of two numbers, right? And now you have power series. So if I am to kind of make this parallel real quick as a side note, I'm going to say it like this. I have numbers correspond to sequences. These are the things you're dealing with. Then you have operations, like addition, multiplication, or whatever. That is your sums, which is series. Let's write series. And then you have your functions, which introduce x. Well, now you have your power series. So these are the roughly the correspondences in how it progresses. So sequences is just like counting numbers, and then series you add them, and then you add the power series. And you see how picking the x over here changes what the series do. Which would be the same thing, right? When you are writing the function over here, your y depends on which x you pick. Well, over here, convergence and divergence depends on which x you pick. So that is in the function in some sense. All right?
I have a question.
Yes.
Can you explain how that 5/4 proves that x equals 7 is not a good value for this?
Because it's larger than 1 by geometric series. When r is larger than 1, you get divergence by geometric, right?
That's right. Yeah. No, that's what it was.
So I picked 7, which was in a divergent outside of the interval of convergence. So whichever value for x, and guys, these are the values for x, right? In the interval of convergence, you are picking those x's. So you singled out x's that will make this power series converge. You pick outside, it will diverge. Yes?
Isn't going to be the absolute r greater than 1
What happened?
for the divergence?
Yes. Mm-hmm. And then you have to do the or, right? Because greater than 1 in the absolute value, when you break it apart, you can't write it as a compound 1 like this. You have to write it into two separate and write or. But there is really no reason to do that. Because once you get this, the complement of that is the divergence. So anything that is outside of this will be divergent. One more example. Summation 1 to infinity k factorial times x to the k.
By the way, timekeeper says you have 45 minutes left.
And then I die.
And I will be bugging you tomorrow morning first thing to post these notes. Since
All
you
right.
can't do it right now.
So, thank you. So, I don't know why I'm so terrible. I shouldn't be. I appreciate it for another 3 weeks. Thank you.
Namaste.
What was doing? Oh yeah, problem. So limit k goes to infinity. We have our k plus 1 factorial x to the k plus 1 divided by k factorial x to the k, which is the limit k goes to infinity, peel off. So we have k plus 1 times k factorial times x to the k divided by k factorial x to the k. Kill. And we get limit k goes to infinity, absolute value k plus 1 k plus 1 times x, that's it. K plus 1 times x. We kick x outside because limit operates only on k's, and we get limit of k plus 1 as k goes to infinity. What happens there? Exactly. We get x times infinity. Well, unless x is 0, right? In which case we have the convergence. Would we agree on that one?
Can you repeat that again? Unless what is
unless x is 0. So this is going to be convergent only at one point, x equals 0. For x equals 0, we have convergence. Everywhere else, we have divergence. So this one is convergent at a single point. Yes. Give me a second. So converges only at x equals 0, which gives us that the radius of convergence is 0 as well, because we are only talking about a single point. Now, let's just quickly look at this. So, yes. So for factorials, if we have k plus 1 factorial, that's k plus 1 times k factorial. So think of this as the 7 factorial would be 7 times 6 factorial. 7 factorial has 1 through 7 multiplied. You peel off 7, you still have 6 through 1 multiplied, which is 6 factorial. So you can always peel off whatever you need. Making sense? You can peel off as many as you want. So I can write n factorial as n times n minus 1 factorial, because I peel off n. So if this is, let's say, 5 factorial, it would be 5 times 4 factorial. You always have to have 1 through n multiplied, all of the integers. So if I peel off one of them, all the other ones stay in the factorial below. Make sense? Awesome. Done.
Ah, thanks a lot.
You're welcome.
I was writing that down.
I'll repeat.
Only because I was putting a reminder in here while you were writing that.
What's that?
Just do undo.
Oh, yes, you're right.
Undo, and just leave it there. Okay, thank you. And you just move on from there, leave it in the notes. That's okay, you don't have to get rid of it. It's in purple, so we all know it's a side note. Lost Anna.
No, I just
What is
make.
that last one? Is that a 4?
Yes, 4 factorial.
Okay.
All right.
Purple side. No, thank you.
You're welcome.
Just leave it there. It won't hurt anything if you leave it there.
All right, fine. Okay. To address your question about the 0, I will make sure over here a 0 to the k, right? So we have 0, 0, 0, 0, 0, 0, 0 times whatever. K factorial is always 1. 1 times 0, 1 times 0, 1 times 0. 0, 0, 0, 0, 0, add 0 infinitely many times. We're good to go, right? Awesome. Okay. Let's take a look at one more example from, let me just see, is anything else? So we talked about the interval and radius of convergence. They give a spicier problem. Oh, I want to do this one. And then they jump into 9.4, so they can actually talk about it again in 9.4. Okay. So next concept is combining power series. You know how you can add two functions and get a third function? You can divide them, you can multiply them, square them. Or you can do function composition, plug one function into another function. You can do all of that with power series. You can add them, subtract them, multiply, divide, square. You can also nest them one into another and have a double sum on it with the different counters. So summation of m and n, and then they operate on each one on their own. You can make them 2D, 3D. You can do whatever you want with these power series. We are only going to look at the sum and difference, multiplication by a power, and composition. So we're not going to go into gory details, but you guys will, those of you interested in mathematics, pursuing mathematics later, you will see all the other wonderful things you can do. Yes, I did say wonderful things you can do. So what do we have? Sum and difference. So we can combine power series like this, ck plus minus dk of x to the k, and that will converge to f of x plus minus g of x. So we know that the power series, right, give us functions at the end. This is extremely important result for the differential equations. You are going to have a chapter on differential equations on power series solutions to second, let's say, order differential equations. And most of them will have sines, cosines, or hyperbolic sine, hyperbolic cosine, or e to exponents in the answer, or combinations of those. And you need to be able to kind of separate terms from which ones go with which, and then you can put the sines and cosines together. Multiplication by a power, combining two power series. So another important one for differential equations, when you're talking about Euler's equation, this is the way to solve Euler's equations in diffuse, when you multiply power series by x squared, and then that absorbs inside. So multiplication by a power, we are talking about having some kind of an exponent in front of this ck x to the k, and then this gets absorbed inside, and you get ck x to the m plus n, sorry, m plus k. Why can you pull this? You can't do this with integrals. You can't pull x in and out of the integral. But remember, integral is the operator which operates on x. Summation is the operator which operates on k's. So this xm can go in and out as it wants. It doesn't matter. You are not allowed to pull this x out because it's to the k. And this operates on k's. So this one is stuck to be inside forever. Sounds obvious, right? But this one can go in and out as it pleases, right? You made some guards. I don't know, whatever. And number 3, composition. Oh, this one is important for this class, okay? For this class. It's going to be a question on a test 3, 100%, and then possibly on the final. So h of x is equal to bm, x to the m, sorry, where m is positive integer and b is a non-zero real number, the power series, okay? So this is, okay, summation ck of h of x to the k it's too complicated the way it's written. Trying to see if I can actually make it look better, easier. Because this b doesn't show up, and let me see if I can give a easier. You know what? Composition. Example. It's going to be much easier for you to get it this way because the way it's written is a little bit convoluted, and you can read it in a book. But here's the example. Expand power series expansion. Expand e to the x squared. Step 1. E to the x is, as you know from before, what? 1 plus x squared over 2 plus. We got this, right? It's x over the factorial. Replace every x by x squared. Function composition, guys. You replace every x with g of x. So this is exactly what we're doing, and we're getting the power series ex squared is actually 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6 plus dot dot dot. Does it make sense? So function composition of power series, we can do this. What I'm doing is I look at e to the x squared. Have no clue how this looks like, but I know how e to the x looks like. So if I can just, I write the expansion for e to the x, and then I replace every x with x squared, and I do the arithmetic or algebra, whatever you call it, to come up with a thing. And that's it, done deal. That's the composition. Now this is the one that we are going to need in this class, because of the very last thing, and that is actually 9.4. Let's go with differentiating and integrating power series. At which point I should start the new stream and the new tab and all of that stuff, but I won't.
Differentiation and integration power series.
Yes, of power series. Of power series. Is the word "of" missing? There it is. So 9.4 starts right here and ends in the next 10 lines.
Let's hope so. I'm running out of pencils.
We differentiate. Oh, and integrate term-wise. 9.4 over. So 9.4 is a combination of composition and this sentence that you are differentiating term-wise. So let's see a cool feature. I told you earlier that sine x is expanded. Sine x is expanded as what? X plus, sorry, minus, you're right, minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot, dot, dot. Are we agreeing on this? Let's differentiate. What's the derivative of x? 1. Minus 3x squared over 3 times 2 times 1 plus 5x to the 4 over, yeah, I'll just want to write 4 factorial because I'm lazy, minus what is this? These guys cancel. X over 2 factorial plus over 4 factorial.
So what's this next row doing?
I'm just computing.
Oh, you're computing, okay.
This is how awesome power series are. Have you wondered before why derivative of sine is cosine? This is the stuff you should bring up for the Thanksgiving dinner.
And then what if you integrate it and make it 1 times 1,
Plus c.
and then you put the negative sign?
Yes, because it shifts. There's a negative sign there, right? Yeah, math makes no exceptions. It's always beautiful. Now, if you are to take the derivative of cosine, you should get negative sign, right? Well, this one dies, right? The first one would die, look number 1. And then you see that the next term is negative. So negative cosine when you factor out minus. Negative sign. It just works. You can't escape it. It works. It fits perfectly every time. Every time. Exactly.
Oh, sure, yeah.
Because you will definitely always remember the expansion for sine. It's much easier than remembering anything else. Clearly, sine x is written as the summation of x to the negative 1 to the k of x to the 2k minus 1 divided by 2k minus 1 factorial. That's obvious, right? If you start with 0. So clearly that's your expansion. This is what you remember. And next time someone asks you something, especially if you're tutoring, right, about trig, have everything there. Do we also notice what else you were forced to memorize something about sine function and the cosine function, and you really didn't know why? It was just told to you a property of sine and cosine.
They're oscillating between negative 1 and 1.
That's true,
But that's not the one you want.
Can you remember this? A property of sine function and a cosine function that you were told to memorize. Most of those you have proofs for. There was one that was not discussed at all. It was, I said, here, memorize these 2 things and you're done.
Inverse.
Nope. Yeah.
Odd even functions.
Odd even is the only thing that was never discussed. They say, oh yeah, it fits the formula x minus 1, right, minus x. You just said it fits that. Remember it, memorize it. It was never told you that why they're even and odd functions. Well, odd function, right? Sine is odd, and look at the cosine. Even.
Oh,
I know. Calc2 is so awesome. Power series are amazing. So now you know you have that piece of the puzzle. Next time you tutor someone in Precalc2, they ask you why. You have 30 minutes to fill in.
Somebody asked me that, and I spent like 5 minutes trying to figure out reason why.
Well, you're welcome, my friend. You are welcome, my friend. All right. I like to finish. So this was 9.2, and now I'm finishing 9.4 because that's 9.4 technically. You know when you have the fireworks and there's the grand finale? Yeah. Look at this one. How much did you love this problem? Do we all remember it?
yes.
Great.
I remember hating it personally.
So the way you solve this is you write first 3 terms of e to the x. The first 3 terms of this is power series. Those are polynomials. You FOIL those, and you integrate like this.
What? I did not follow that at all.
You write first 3 terms of this one, which is 1 plus x squared over 2, right? And then you write first 3 terms of this. You get
Okay.
polynomials, and then you just FOIL that, and you integrate. And none of that stuff that you have to do with 2 integration by parts and shuffle the terms left and right, and this is how it's done. So try it. Try it now. Expand. So you know the expansion for e to the x. You know the expansion for sine x. Write 3 terms each. FOIL, you will get 9 terms. And then just integrate polynomial and then put plus c at the end, or minus 1, whatever.
Question.
Yeah,
Are you moving this on there?
I will.
Okay, because I'm still, I'm still not feeling great, so.
But yeah.
I'm trying my best, I really am.
it sufficiently annoying?
I guess less annoying than by parts. Twice. What? Just integrate now. Nothing, that's it. You're done. So technically, we have 1 plus x squared over 2 times 1 minus x cubed over 6 plus x to the 5 over 120 dx. X, that's what I said, please pay attention. It's clearly an x.
Yeah, I see that.
Oh,
All right.
oh,
No, that was just my magic trick,
your magic trick.
making everything disappear. And this equals to integral of FOIL dx, and then answer. Plus c. I'm very fast with these answers. Now I do have to address one of the issues here, and that is what happens if you have the same integral, or here e to the x squared dx, but you want to compute this integral at let's say 4 to 5, right? Well, at this point, it is very important to realize that you actually have to center your expansion at 4. All right? That's very important, because you cannot, you are dealing with a definite integral, and the definite integral is going to be computing numbers and computing variables, computing numbers and values, right? Area under the curve. So you cannot expand the, just go and say, okay, it's 1 over, it's 1 plus x over 2 plus, right? Because it's that assumes that you're expanding around 0. But expanding around 0, and you will be computing at 4 and 5. That's far away. So your answer will be far away from what the answer should be. So you will actually expand around 4 in this case, and then you will integrate. Now you cannot integrate this, guys. You cannot integrate this one because it doesn't have x in front for u sub, right? It's not any of the techniques that you. So you have to do it this way. You have to use power series to do it, and expansion has to happen around 4. So your e to the x expands as 1 plus x squared over 2. You can put in another term if you like, pain, and it's going to go forever. And then you realize that you have to shift everything 4 units, and then you have to square it. So it's going to be e to the x minus 4 squared, and then 1 plus x minus 4 squared plus x minus 4 to the 4th over 2 plus x minus 4 to the 6th over 6 plus dot dot dot. You pick how many terms you want to use, plug them in the integral, and then good luck with that. So
Do you do the same thing for the 5, the upper?
no. Just
only do it for 4?
yeah. Oh, there's a lot of other stuff that's coming up later in mathematics. So these are some of the introductory. There are courses and courses on series, actually. There are Fourier series, Lorentz series. There are different types of series later on down the line if you get interested in mathematics and pursue graduate and so on. Just
How many terms should you get?
remember the rule of power series. The more terms, the better precision. So you have to make an educated guess and say computation against precision, right? It's like quantum mechanics. You can know the position and the speed. You can either know precisely position or the speed. You can't know both. Right? The more precise you know one, the less you know the other. You make trade-off here. As you pick more terms, it becomes progressively worse. Remember your previous example. I picked 3 terms each. When you FOIL them, you get 9. If I picked 4, 9 jumps into 16. You get better precision, but you went from 9 terms into 16 terms. You can go back, right? Because technically, e to the x on its basic level at 0 is approximated by function 1 and sine x with x. So technically, one term approximation for this is just integrating x, which is x squared over 2. That's going to be much worse than what you have with your 9 terms, or 16, or the next one, 25 terms, right? So we program. You use Java, you use whatever programming language, well, within MATLAB most likely, to program these things in, because you don't want to do these things by hand. And then there are graduate courses like Asymptotics 1 and Asymptotics 2, which would have these nest in each other, and then you expand the series within the series, and then, right, so you keep dragging 5 terms in a nested. You get 500 terms on a second step. Yes?
So for the purpose of your test, one would want to stick to expanding to 2 or 3.
On the exam, I will most likely say expand 3 terms, be done.
Okay.
With the bad mood, it's going to be 4. But with like really bad mood, then it's 4.
Well, we all love you very much, so we're going to be in a very good mood and make it 3. Or even better, 2.
I'm done with 9-4. This is 9-2 and 9-4 together. 9-4 does also say take limits of these things as well, which is term-based again. So nothing special. Did anyone look at the title for 9-3? It's called Taylor series.
The Taylor series all over.
And what have we done so far? A Taylor series for 2 classes. So I guess we're just going to, well, we'll do Taylor series as a review technically next class again. On when is the next class? Monday. So Monday, 9-3, but we are not introducing anything new. They're going to repeat the formula. They're going to ask you to compute Taylor series for non-standard functions. Introduce binomial series, which is not a big deal. Literally 20 minutes of work, because you already know power series. You know the Taylor series from 9-1. You already have the definition. You should know definition by now, right? The nth derivative computed at a divided by n factorial times x minus a to the n. You already know that. You should know that. All right, so that's it for now. 9-2, 9-4 done. We'll talk about 9-3 on Monday a little bit and be done.